All right, what we're looking at today is called the fundamental theorem of calculus. And there's not a whole lot of fundamental theorems in mathematics, so that should emphasize the importance of this. So what we're looking at here is I want to find the area of the small little strip in here. So we're going to try to work out what the area of that is. We've got some generic function, and we're going between x and plus a little bit more than x, plus this h. Well, we could think about this as it's going to be somewhere between that right-hand side. So it's going to be less than or equal to the rectangular rule on the right-hand side. So that would be a width of h and a f of x plus h, because it's the height at x plus h. And it's going to be bigger than the rectangular rule at the left-hand side, which would be h times just f of x. So we know it's going to be bounded in there. And for the more technical minded ones, yeah, if it was, this is a increasing function. If it was decreasing, then I'd have to swap those two around, but that's all right. And in theory, I could have a section that had a hump or a dip in it. But as long as I pick a small enough h, I can avoid that. I'm sort of glossing over that as a technicality. So let's say I had a function that would give me the area all the way up to any value, and we'll call that a capital F of x. And if I had this function capital F of x that gave me the area all the way up to a point, to get this little bit in between, I'd want to look at the difference between those. I'd want to say the area up to f plus of x plus h, and then minus off the area up to x. And so I end up with a little formula like this, saying that this supposed made-up function, capital F, gives me the area up to this point, and because I just want this little strip in the middle, I'm going to say that it's capital F x plus h minus capital F x. So I've taken the area all the way up to here, all of this, minus the area here. Now, a little bit of rearranging here, and I'm just going to write this in black now. So if I divide through by h, f of x is less than capital F of x plus h minus f of x over h. And now I'm going to take a limit. Now I'm going to take the limit for every single one of them. I'm going to make that h smaller and smaller and smaller, and see what happens when I get that smaller and smaller bit. So limit as h goes to 0 of f of x is going to be less than or equal to limit as h goes to 0 of capital F of x plus h minus f of x all over h, which is less than limit as h goes to 0 of f of x plus h. Now, what we notice here, well, the limit here as x goes to h, there's no h in here, so that doesn't change. And this bit here, when h goes to 0, well, I get x plus 0, so f of x. So I've now got this area bounded by two things that are the same thing. So that must equal, this stuff here must equal f of x, because it's in between. And we will recognize the bit in between as a derivative. That means that whatever my function is that gets me my area, when I derive it, I get my function.